Hey everyone. For this session, we're going to be talking a little bit about the scientific methods that we are going to hopefully be using throughout the course. So this isn't something that we're going to be focusing too much on specifically, but more generally, whenever we talk about different aspects of the course, we want to be seeing how the scientific method applies. And this is going to involve things like demanding evidence, saying, I'm going to withhold accepting a claim until there is sufficient evidence. How do we go about gathering that evidence, and how do we use that evidence to try to reach reasonable conclusions? So, as I mentioned before, in astronomy, we use basically all other areas of science: physics, chemistry, geology, and hopefully one day biology. And one of the really interesting things about astronomy specifically is that we can actually use astronomy to study those other fields as well. We can use physics and chemistry to inform our understanding of astronomy. And then we can also use astronomy basically as a literally universe scale lab to study more of the properties of physics and chemistry. So in astronomy, we can look at some of the most extreme physical conditions, say the conditions near a black hole, the conditions in the very early universe, conditions that we just can't reproduce in the same way in a lab. And again, this can allow us to learn more about physics. And we learn about astronomy and all of these other sciences using scientific methods. So let's talk about that a bit. When we talk about science, when a lot of people think about science, they think of it as, oh, here are a whole bunch of facts. Like, this is the mass of the moon. This is the food chain. These are a biological process that goes on in the human body involving proteins and things like that. But that's not really what science is. Science is a method that we try to use involving proposing and testing hypotheses to try to develop models of the universe around us, models of different kinds of physical systems that have predictive power. So it's a method based on proposing and testing hypotheses. You've probably seen something like this before, something with the scientific method of make a hypothesis, develop an experiment, perform that experiment, check how the hypothesis is. And the actual methods of science are a lot more kind of disorganized than that, disorganized in the best possible way. There's still the key idea of, well, I observe some sort of physical phenomenon going around. I try to look for a pattern in that data and try to hypothesize, I think that this pattern will reliably produce results that match experimental reality. And using that, we can develop models that allow us to make predictions about future experiments or future observations. If our model makes a certain prediction, well, then we can put that prediction to the test and try to falsify this model, see if we can really test this model, see if it'll break. It makes me think of a kid building a tower of blocks, and then another kid coming by and saying, I'm going to test this tower by just kind of poking on it a little bit more to see when it will fall over. The better the tower, the more it will be able to survive that kind of a poking process. Because these models, when we make a prediction, if we then go out and do an experiment or make some sort of observation, and that prediction that we made does not agree with observation, well, then we have to go back and develop a better model. We have to either revise or reject the model we had and come up with something better. If our model makes a certain prediction and we go out and do that experiment or make that observation, and the results of that experiment or observation match our prediction, great. Make another prediction in an even more extreme case. And this is a continually refining process. Sometimes as we're developing models, we find deeper ideas, things like conservation of energy, the concept of conservation of energy that applies to many other systems that we thought were very different from each other. We find more kind of deeper underlying laws, theorems, relationships. Sometimes as we're coming up with an experiment to actually test his prediction, maybe that changes something about how we look at that model. This is a lot more kind of all over the place sort of process. And again, this is a continually refining process. There is no point that we're ever at where we say, okay, we've got this model, it works, and we're done. In science, we don't make truth claims. We say, I have a model of some kind of physical system, of some aspect of reality, and tentatively, it is the model that best explains and best describes the observations that we have for it so far. If new observations come in that contradict our model, well, then we have to either revise or reject that model. This is part of it being a continually refining process, and it means that we're not always guaranteed that the models that we have are going to be right. In fact, we're always expecting those models to be overthrown at some point. But every time we come up with a better model, generally we go in this direction that things are improving. We have this method for improvement. When we talk about a scientific hypothesis is a proposed explanation for some set of observations or some set of experiments based on scientific principles that is testable. And in a lot of circumstances, at least for certain scientific questions and certain scientific hypotheses, these can very effectively be kind of proposed in an if, then, because statement. If I do this thing or make this observation, so we have some sort of conditions where I can put this idea to the test. If we do this, then there's going to be some specific outcome of the experiment. So when we make a hypothesis, it has to have this testable nature. If I do this, then this is going to be the outcome of that observation or experiment. Because, and then we go into the details of what are the underlying principles. This idea of testability and specifically falsifiability is absolutely crucial in any kind of science. We always have to have the ability to have our ideas be proven wrong. So again, this is kind of expanding on that. So in order to be testable, we must express our hypotheses in terms of falsifiable statements. So what is a falsifiable statement? A falsifiable statement doesn't mean that the statement is false. All it means that there is, in principle, some observation or some experiment that we could do, that we could go out and make, where if the statement is false, we can demonstrate it to be false. So, for example, the statement, there are 5 fingers on my hand. That is a falsifiable statement because I could take my hand and say, I'm going to count up how many fingers I have. 1, 2, 3, 4, 5. Okay, that statement survived that testing. If I, had an extra finger, or if I had, lost a finger or something like that, I could still do that experiment of looking at my hand and counting how many fingers do I have. And if there weren't 5 fingers on my hand, I could disprove that. Value judgments are often not falsifiable. So, for example, the statement, Macs are better than PCs. Well, are you talking in terms of processing power? Are you talking in terms of their cost? Are you talking about whether they're better in terms of the programs that are available for different applications? Are you talking about IT support, customizability? Unless you're being very, very specific, value judgments are generally not going to be falsifiable statements. Another unfalsifiable statement might be something like, the last thing Abe Lincoln was thinking about was the fiscal budget. or something like that. We can't answer that because there is no current or foreseeable technology that would actually allow us to test, to put that statement to the test. Okay? So again, a good scientific hypothesis must make specific predictions that can be tested and could be disproven. The quality of a scientific idea, of a scientific hypothesis, is based on how many specific predictions can it make, how many opportunities are available to disprove that idea. The more disprovable that idea is, the more opportunities we give it to be disproven. If it survives that kind of repeated testing, then we have a pretty good idea. So again, hypotheses must make falsifiable predictions. So for example, we have, let's consider the ancient Ptolemaic geocentric model of the universe, where the Earth is at the center of the universe and all of the planets orbit around the Earth. All the stars, all the planets, everything's orbiting around the Earth. At a certain time, when we had less information, that might have been a reasonable conclusion to reach. Like, I don't feel like I'm moving around. I see the stars change over the course of the night. I see the sun move across the sky. Same thing with the moon. It seems like it could be a reasonable position that everything orbits around the Earth. However, when we get better data and make observations like when Galileo developed the first early telescope and identified the moons of Jupiter, for instance, the moons of Jupiter, you could see the planet Jupiter, and a bunch of moons were orbiting around it. So that was something that wasn't orbiting around the Earth. Also, with Galileo's telescope, looking at the phases of Venus. The phases of Venus, as predicted by this Ptolemaic Earth-centered model of the universe, do not match the phases of Venus that were actually observed. Okay? So that causes us to have to reject or at least significantly revise our hypothesis, any hypothesis that is falsified. So we keep the ones that survive repeated testing, and we reject or revise those hypotheses that are directly falsified. And again, this is a continually refining process, and we actually find that we learn the most when we prove our ideas wrong. Okay? So let's consider a specific case. Let's look at gravity for a second. I'm going to stop my share so we can zoom in on this a little bit more. Let's consider gravity. Let's say I've got a couple of objects that I can drop. Okay, so I've got a larger mass and a smaller mass. You might ask, well, which one, if I drop them at the same time from the same height, which one will hit the ground first? Okay, so maybe make a prediction. I'm going to drop both of these at the same time. Hopefully you can see it on the camera. But think of which one's going to fall first. So got the two. Oh, my camera's getting a little bit easy. Let me see if I can reset my camera. Stay in focus. Why is my camera going so terribly out of focus? Stay. Okay. So let's say I'm dropping these from the same height at the same time. Let's see which one hits the ground first. 3, 2, 1, drop. Even though this one is about 25 times more massive than this one, you can actually see that they hit the ground at the same time. So 3, 2, 1, drop. They hit at the same time. Okay, so it looks like, well, let's continue this testing. So maybe I'll try, what do I have here? A stapler and my cell phone. So you got a stapler and a cell phone. I'm going to try dropping these at the same time. 3, 2, 1. Okay, so they fall at the same rate. Let's try some other ones. I got my calculator and this little kind of squeezy brain toy. Let's try this. 3, 2, 1. Okay, so all of these objects, it seems like all of these objects, when released from rest at the same height, they fall at the same rate. But again, that's only going to be a tentative conclusion. So let's try another one. I'm going to try this little mass again and this piece of paper. So let's try this. 3, 2, 1. Well, Now, those didn't fall at the same rate. So why didn't these ones fall at the same rate? When I drop them like this, that takes a lot longer to go down, but let's say I took this piece of paper and I just crumpled it up. Hope there was nothing important on there. If I do the same thing, 3, 2, 1, drop, now they fall at the same rate. So we have to revise our idea because we got new information. In this case, we got the information that when the force of air resistance becomes significant, like on that large, low mass but large surface area piece of paper, air resistance is going to have a greater effect on that piece of paper than air resistance is going to have on the small little dense mass. So we have to revise our ideas. But we can all agree that if I took an object, if I took two objects and let them go, they would both fall, right? I think we can agree on that. But what if I had a helium balloon? So in the case of the helium balloon, we'd have to figure out the effect of the buoyancy force of the air. Or if I attached a rocket to something, we'd have to figure out, what effect that has. So again, the thing I want to point out here is that science is a continually refining process. All of our ideas are tentative and subject to revision. And it's only when an idea has survived repeated testing that we increase our confidence level that that idea is accurate. So again, we learn the most from these kinds of unexpected results. So a couple of things about just some of the hallmarks of science. Modern science seeks explanation for observed phenomena that rely solely on natural causes. So again, we're trying to explain things that we see in nature. Let me say something about this natural causes. This idea of natural causes is related to repeatability and consistency. For example, if I do some experiment, let's say I mix some chemicals and there's a certain chemical reaction. And let's say I try to mix those chemicals again and see in the same way, but something else happens. Do I know what caused that change? Well, maybe it was a temperature difference. That's something I can measure. We can say, is it the same temperature? Try that. And does that make them match up again? Maybe, maybe not. Maybe it's something about the relative humidity. Maybe it's something else about, the materials that I'm mixing together. We can start going through these, but what if I said that the thing that was causing this chemical reaction to run differently, what if I said that that was a ghost? Well, how would we try to isolate and measure the variable of the presence of a ghost? We can't really do that, at least with any method or technology so far. This is part of what we mean by natural causes. At this current point, the methods of science don't really have any way of testing things like supernatural causation. We have to be able to test the experiments, do those experiments and do those observations under the same conditions every time. If there's some supernatural effect or some supernatural agent that's affecting our results, we can't really do anything with that. We can't move that needle forwards at all. If I said a ghost was causing, this particular thing, well, I don't really have any model to build with to say, well, what else is that ghost going to do? So that's some of the reason why we talk about saying, at least for now, until we develop new methods, we have to kind of limit ourselves to looking at natural causes. Other ideas. Science progresses through the creation and testing of models of nature that explain the observations as simply as possible. And this, you might have heard of Occam's razor before. The simplest explanation is usually the correct one. Now, that's not exactly what the formal definition of Occam's razor is. A little bit better way of thinking of it is which idea, if I have two ideas that are trying to explain some physical phenomenon, And both of those ideas are equally good at explaining those ideas. Which one requires fewer assumptions or fewer kind of tweaks to the model to make everything work correctly? Which one requires fewer assumptions to be able to make those predictions? And we lower our confidence in the one that requires additional assumptions to be made. So that's kind of what Occam's razor is. If we don't have to make an assumption about something, let's try not to. And lastly, a scientific model must make testable predictions about natural phenomenon that would force us, again, to revise or abandon the model if the predictions do not agree with observation. We have to be able to put this to the test. When we're thinking about why do we care about science? Why do we care about having these accurate models of nature? There's a lot of different answers to that. One that I kind of like is, in our everyday lives, there are sometimes outcomes of situations, events that we want to have happen, and sometimes outcomes that we don't want to have happen. Okay. So if I have a model that says, well, depending on what I do, I can get one of those two outcomes, I now have the agency to say, well, this model says if I do A, this will be the outcome. If I do B, this will be the outcome. And I can choose between doing A or B. But that only works because my model predicts two different possible outcomes depending on what the input is. It's not like if I do something, it could still be either one of those two outcomes. We don't know. When we're talking about ideas that are not falsifiable, an idea that's not falsifiable, like, let's go back to the ghost example. If we said, the reason that objects fall are that ghosts push on them and they push on them by different amounts. Well, I don't really have any way of testing that to say, well, what if the ghost decides to push on it a different amount? We lose our ability to make predictions of nature and say, and if, let's say I dropped this and it moved up instead, oh, the ghost just pushed it up instead. The ghost idea could kind of explain anything. And if you can explain anything with your model, it's a predictor of nothing. If it could explain any possible outcome, then we have no way of figuring out which of those specific outcomes we're actually going to get. So it can't predict anything. So again, that's part of the reason why we always have this requirement of falsifiability and predictability. Can we use this to predict the outcome of new experiments? So, talking about scientific theories briefly, a scientific theory is not the same as a hypothesis. When you hear the word theory in just kind of everyday conversation, pause the video for a second and just think of what sort of ideas kind of come to mind when you hear the word, I have a theory. So you may think of things like, I have an idea, I have a guess, I think this is going to happen. A lot of things that we might not put a super high level of confidence on. In science, the word theory is used in a much more rigorous way. In order to be a scientific theory, it has to have explained a wide variety of observations with as few simple principles as possible. So kind of throwing in a bit of Occam's razor there. It has to be supported by a large and compelling body of evidence. This one is a little bit subjective, like what you find to be a compelling body of evidence and what I find to be a compelling body of evidence might be a little bit different. So it's a little bit subjective there, but should reach a fairly high bar. It has to have not failed any crucial test of its validity. Okay? So it has to have already been tested and has to have passed all of those tests that we've been able to devise so far. Now, this does not mean that we're like, this idea is absolutely bulletproof, it's untouchable, we know that it's absolutely true. It does not mean that. If we have some new observation that comes along and it directly contradicts the prediction of our theory, you can bet that scientists are going to be checking the work, seeing that contrary observation or contrary experiment actually is reliably giving those contrary results. But if it stands up to scrutiny, then that theory, again, must be either significantly revised or discarded. Okay? And the gold standard of this is, has your idea predicted some new phenomenon, some completely new property that has not been detected yet, and then we go out, look for that phenomenon, and find it. That is the gold standard of a scientific theory. So let's look at an example as gravity just being a theory. Well, let's see how it matches these things. Our understanding of gravity, and we're going to be talking about this later on in the course, it can describe things like motions on the Earth. So things like projectile motions. We can use our idea of the theory of gravity to describe everything about motions on the Earth. And probably should have started with this. What is this kind of Newtonian theory of gravity? Well, here's the idea. If I have two masses, two objects with mass, they will attract each other through this gravitational force. The greater the masses are, and the closer those masses are together, the stronger the gravitational attraction, and there's an equation that goes long to describe how strong that attraction is. That's it. That's the whole theory. Larger masses, closer together, have a stronger gravitational attraction than small masses further apart. But with that, we're able to describe things like projectile motions on the Earth. We are able to describe the orbits of the planets around the sun. We are able to look at the structure of stars and planets and figure out, well, why does a planet have a spherical, oblate, spheroid kind of shape to it? Why do stars have that kind of shape? We can look at the structure of galaxies and identify how gravity is describing those motions. We can use this to launch spacecraft from one planet to another. And again, it's all based on those simple principles of masses attract each other. The greater the masses, the closer they are together, the stronger the attraction. So it hits that, explains a wide variety of observations, and is supported by a large and compelling body of evidence. And has been tested many times and not failed any crucial test of its validity. Let's talk about this one for a moment. In the late 1700s and the early 1800s, astronomers had been looking at the motions of all the planets in our solar system that were known at the time and checking their observed orbital motions against the predictions of Newtonian gravity. So we have something like, the sun in the middle of the solar system, and we are looking at these planets that are orbiting around and seeing how close they match up with observations. And to the limit of our experimental accuracy, those planets all match except for the furthest known one. The furthest known one, it was almost an agreement, but just doing something, slightly different. So acting in a slightly different way than was predicted by Newtonian gravity. Well, this leads us with a couple of options. One, our understanding of gravity, the Newtonian theory of gravity, that could be wrong. Or there's something that we're not accounting for in this particular physical system. And some astronomers were thinking, well, maybe there is another planet even further out that's giving some additional gravitational tugs to this planet and is throwing off that motion in a particular way. So over the course of decades, the motions of all these planets were being monitored, and astronomers were trying to identify if there's an extra planet out there, where is it, what are its properties, and how can we find it? Okay. And I think this was in the 1820s or 30s, I forget exactly when it was, astronomers had finally compiled this data and said, well, there should be another, if Newtonian gravity is right, there should be another planet out there, and on this night, in this direction of the sky, you should be able to find it. And within 1 degree on the sky, a tiny little area on the sky, that is how the planet Neptune was discovered. The planet Neptune was discovered just by using math and saying, if the Newtonian theory of gravity is correct, there should be this extra planet out there giving these additional plugs. This was the planet Uranus, the one that was furthest known at the time. That is putting your money on the table and saying, if my idea is right, here's a large bet on some completely undiscovered phenomenon. That's what I mean by the gold standard of a theory, is to make a new prediction that has not been observed or measured before, and then going out looking for it and finding that matching up. However, this does not mean that Newtonian gravity is absolutely correct. In fact, later in the 1800s, the planet Mercury, further observations of Mercury found that it wasn't quite following the exact predictions of Newtonian gravity. And it was actually proposed, well, maybe there's a planet that's even closer to the sun. It was tentatively given the name Vulcan. Star Trek fans might, recognize that. But this proposed planet was even closer to the sun, but astronomers couldn't find it. And this discrepancy of the planet Mercury eventually was one of the observations that eventually led Einstein to come up with a new theory of gravity that we call general relativity. So even though the Newtonian theory of gravity was immensely successful at describing a wide variety of observations, predicting new phenomenon, it was ultimately supplanted and improved by Einstein's theory of gravity, general relativity. So again, we learn the most when we disprove certain ideas. What about other models? Let's say we look at flat Earth models. So proposed models for a flat Earth, unfortunately, they fail to meet observation. I got this from a flat Earth website saying the Earth, their model was that the Earth is flat, the North Pole is right at the center, and Antarctica kind of runs around the outside, and the sun acts like a spotlight, kind of orbiting, spinning around over the Earth, illuminating different parts at different times of the day. The problem is that this model fails to match observation. So, for example, their model for summer in the Northern Hemisphere. Well, when it's summer in the Northern Hemisphere gets more light and the Southern Hemisphere gets less light. So their explanation is if the sun is more centered over the Northern Hemisphere gets more light and the Southern Hemisphere gets less light. So that kind of works. But when it's winter in the Northern Hemisphere and summer in the Southern Hemisphere should get more than 12 hours of daylight. So let's look at this model. We've got this spotlight sun. When it is winter in the Northern Hemisphere and summer in the Southern Hemisphere, that spotlight sun should be covering up less than half of the Northern Hemisphere, but more than half of the Southern Hemisphere. Does that seem like this flat Earth model could, with the spotlight sun, could that spotlight sun illuminate? Let me see if I can draw on here for this. Could that spotlight sun illuminate more than half of the Southern Hemisphere, so something like that, but less than half of the Northern Hemisphere? I don't think that spotlight sun is going to be able to match that observation. So that is a prediction that these flat Earth models make that do not match predictions or do not match observations. Another one would be the changes in the nighttime stars in the Southern Hemisphere. We're going to talk about this a little bit later in the course. In the Northern Hemisphere, if you look at the motion of the stars over the course of a night, they'll go counterclockwise around the North Star. If you're in the Southern Hemisphere, they'll actually go clockwise around what we call the South Celestial Pole. This flat Earth model, there's no way of matching up those two observations of how the stars seem to move in the Northern Hemisphere and the Southern Hemisphere. It does not match observation. So again, that's an idea that is proposed. When the idea is proposed, it's worth taking the idea seriously and saying, okay, what testable predictions does it make, and does it pass those tests? These flat Earth models, do not pass those tests. They do not agree with observation. And things like conspiracy theories are sometimes completely unfalsifiable, sometimes by design. You'll sometimes hear with certain conspiracy theories, say the flat Earth model, you'll ask, well, what about these satellites that we've sent into space and have taken pictures of the Earth and it's a circular Earth? Oh, that's just more of the conspiracy. Those are faked. In a lot of conspiracy theories, they're kind of designed in the way that any evidence that disproves the conspiracy theory, conspiracy theorists will take as evidence of a deeper conspiracy. Oh, the data is showing this. Oh, those scientists must be paid off. Oh, this group over here has tried to, do your experiment and they came up with a different result. Oh, they're being paid off as well. That's an example of something being an unfalsifiable idea. There's no experiment that you can do to disprove that idea because you keep on adding in, these alternate explanations of, oh, they're being paid off or lying in some way. Again, a lot of these ideas we're going to be kind of using throughout the term to basically put the ideas that I propose and the claims that I'm going to be making, how do we put those to the test? How do we check their validity? Things like that. So we'll call that discussion of the scientific methods. We'll call that good for now.